Hi, this is the video presentation for the Applied EE project. This video is split up in two portions, one for each task. First, I'll go through building the software, including all the iterations, followed by a demo. I will not be explaining the automated data collection scripts, but you can find everything, including the spreadsheets and source code on my GitHub. Let's get into task 1. Well, my personal goal was to build an algorithm that is able to identify this. Well, my face within this at least. And I definitely succeeded. Let's get into the build. Alright, we're here in PyCharm. We're going to be using PyCharm to develop the Python code with OpenCV. We're going to start by importing the important libraries, OS, OpenCV, and NumPy. Right, I'm going to set up some constants that are going to be useful. Base directory, so this is where the file, and followed by image directory. This will be the image path to the demo image that I'm going to show today. Next, I'm going to read the image with image read, which takes the argument of a path to where you can find the image, and I'm going to show it out using image show. The first argument is the name of the window to create it, and the second one will be the image object you would like to show. I'm going to add the wait key so that it doesn't disappear when you launch it. Running this, there we have our test demo image for today. Okay, next we're going to add the webcam to OpenCV. So we're going to create a video capture object and call it cap. The ID 0 is because I only have one webcam. We create a while loop to always read from the webcam and store it in the frame. We're going to show the frame into a window call capture, and then since this is a while loop, to break out the while loop, we'll have a wait key looking for the character Q. So we run this now. There we have the working webcam image into OpenCV. Next, we're going to perform the face detection. For that, we're going to need a classifier. In this case, we're going to use the pre-included R cascade classifier. We're going to use the default one, and later I'm going to show you a better one, but we're going to use the default one for now. It can be found in this path here. Next, we'll have to convert the frame into a grayscale image and then pass that frame into the detect multi-scale function. Here, it will try and figure out where the faces are based on the image and store it into the faces. We're going to then loop through the faces and then draw eclipse around it. So we run this now. We get the ring eclipse around of where the algorithm has detected my face. I'm going to show you another algorithm. It is called Alt2. Works better. As you can see, the background false positive has disappeared. Next, we're going to work on the face recognition. I'm going to create a recognizer object using the LVPH face recognizer. I include a model I have trained beforehand. Then we're going to pass the location of the faces to the algorithm. First, by creating a region of interest around where the faces can be found. Right, I'm going to pass that region of interest into the recognizer to give me an ID of the user he thinks that is found, as well as the confidence level. Actually, it is the distance, but I put confidence level here so that it's more intuitive. Next, I'm going to create some temporary variables to keep track of the best match that we have found so far. I'm going to loop through and check through some conditions to ensure that the face that we have found now is the best match. Then, I'm going to use the best match location and draw a rectangle around it, and then add the label my name. Let's run the code. And here we can see that my face has been properly detected as well as identified. I noticed a flaw with the way I'm implementing LVPH. That is, if I move further away from the camera, i.e., my face becomes smaller, I quickly realize that the distance returned becomes larger. The algorithm just tends to give a better score to bigger faces and a worse score to smaller faces. This will definitely not work for my goal. So I forgot to record the transition to the next slide, but I'm going to try and work on dlib to use deep learning to do face recognition as well as detection. Alright, next we'll start with dlib and face recognition. First, we'll import all the necessary packages. So of note is this line. This line actually adds the CUDA path for CUDA acceleration to the OS environment due to Python 3.8. If you are using Python 3.6 and below, this shouldn't be an issue. We'll define some constants. We have a mode image and the directory basis here. It's just for reference. And the mode here is so that we make the code dynamic. We'll be able to run CNN and Hawk on the same code. Next, we'll import the test image that we've talked about earlier. Face recognition doesn't use BGR color space like OpenCV does, so we'll have to convert it into RGB. Due to the fact that I'm going to be using CUDA acceleration, my GPU only has 4 gigs of video RAM. Therefore, I need to scale the original image down so that I do not run out of VRAM. Alright, now that we have all of that set up, so this line, face recognition, face locations, actually finds the location of the faces and saves it in boxes. Then we'll be able to use coordinates in boxes. So using this line here, it is in the form of top, right, bottom and left in that order, and then we'll just draw a rectangle over the image with those coordinates. And if we run this now, we'll see that the box actually doesn't line up with the face. This is actually because of this line here. When we scale this down to 80%, coordinates for the boxes are actually the scaled down 80% so that the box is perfectly drawn around my face. Now that we have the image detection working, we'll work on image recognition. For that, we'll need to import the encodings that I have generated, basically the training data, and we'll use these encodings together with the faces that we found in this line, the encodings for this image that we are testing. So to recap, we have an image, we find where the faces are stored in boxes, and we pass that image together with where those faces can be found, and we generate encodings for that image. Now that we have the encodings for the image, we will need to compare those encodings with something. Alright, first we create some list variables that we will use to keep down the name of the face found together with the match percentage. First, we loop through all the encodings that we found from the faces, so it actually generates a list of encodings for each face that it has found. And now that we've got the encodings from the faces, we'll loop through all the encodings that we found, right? And we compare them using this compare faces function. It actually compares the encodings from this image to the encodings of the training data that we've imported. So this returns a list of booleans that we store in matches. We set up temporarily the name as unknown, and then we loop through to check whether there is how many number of trues are there in this match. So for every face, we'll keep track of the number of trues that we have and the number of false. Then the percentages of true will be stored as match percentage. So match percentages is what I'm going to use to benchmark one face against another. So we'll just append the match percentage calculated here to a list again that we have declared on top, and then if there are actually no matches at all, we'll just append 0 to indicate 0% matches, and at the end of it we'll append unknown into the names list. This unknown is just a placeholder because I assume that all faces that we detected are not me, and later on, once we narrow it down to be me, we'll actually replace this with my name. Next, we actually want to find me within this list of faces that we have, so we'll use the same concept as LBPH. We'll find the match with the highest number of match percentage given a certain threshold in this case, and then we'll just append my name John onto names where it is the same index as the highest match percentage. Okay, this would not append my name unless it is higher than a certain threshold, and I've chosen 98.8% here because I found this number to be filters out quite a lot of false positives while not creating too many false negatives. And then finally, we'll want to draw these data basically to an image so we can visualize. We'll use this drawing function. So basically I just loop through all the boxes, which is where the faces are, the names and the match percentages, and just draw them accordingly by putting rectangles on the faces, putting text onto the images. This is actually the name that we found, and then this is actually the match percentage. Remember, this actually is match percentage. This is actually not a distance like LBPH. Alright, and then we'll just run this code, and then we have it my face together with the match box that we found, and my name and the match percentage. Alright, finally we'll add the webcam to the program. We'll include a capture, let's put it here, and for the webcam to work, we'll need to continuously loop the frames that we get. So we'll just put all of the code into a while loop, and we'll just capture the frame, the retrieval frame. Let's just call it image since all the code is already for image, and we'll run the capture, take the reading from the capture, and not to forget to add the breaking statement, or else you'll be forever stuck in this loop. So if we run this now, we see that software is working fine, and then it's tracking me quite well and able to identify that it is me. Also, since that we've coded the mode as a variable here, we can easily change this to CNN detection mode without changing any of the other code. So just by running this, we bring up the result for actually running in CNN mode. And CNN mode actually is the final form of the solution developed by me. It detects me quite well even though I'm half-faced among a whole group of other faces. Firstly, look at these results. The algorithm performed impressively. With the F1 score of above 95% across the board, you can find details of this in my report. LBPH lacks the complexity that deep learning certainly has. Moving to task 2, I wanted to create a system that can function in real time and able to detect any symbol with the same script. I do not want to be able to have to tell my program what symbol to expect. The whole solution should just work. Let's build it. Alright, next we're going to work on task 2. Task 2 involves symbol recognition, and we're going to use feature matching for that. OpenCV has built-in feature matching functions that we will use. First of all, we're going to import the required libraries, nothing new, and we're going to set up some directory constants that we can use later on in the program, right? So I have set up some directories to house all the templates as well as the challenge images that we're going to try out today, right? First, we're going to read the two images. One is the template image T, and the other one will be the challenge picture image C, right? Followed by that, we're going to create the object. Op will be the matching algorithm that we're going to try. And so we're going to create the object here, and then we're going to ask op to detect and compute the features of image t, the template first, and store it in KP, and that's KP standing for key points, and that's standing for descriptions, right? And we're going to do the same for image C. We're going to need 2 sets of these so that we can compare them against each other. Once that's done, we're going to create a matcher object, right? We're going to use the brute force matcher. We're going to turn cross check to true so that we can reduce the amount of false positives. I'll show you what happens when it's false. After that, we're going to ask the matcher to match the 2 descriptions from C and T, so that's the challenge and the template image, and then store it in a matches list. Right, we're going to sort the matches list according to a key, and the key is going to be distance, because the match object actually has a few I would say objects in them, and one of the keys is distance, and we can use that to sort the results so that it will always show the lowest distance first to the highest distance. Right, so now that we actually done the entire matching, but there's no way to visualize this because everything is in numbers, so we can actually create a function. I've pre-written this. It's called show results. So all it does is actually it takes the key points of both images and then plots it out using this draw matches function. All this is actually built into OpenCV. Then I'll call the show image function and followed by wait key so that we can actually visualize the result. So let's run this. There. Op is very fast. As you can see, there are actually many matches from our template with challenge picture on the right. Next, I'll show you what happens if I turn cross check to false. Now we run this again. You see there's a whole slew of matches that doesn't really line up. What cross check does is it makes sure that when I match a point from here to here, when I try to go the other way, which I match from here back to here, it is also the same match. So it gets rid of a lot of the one-way matches, so you can sort of say that it only allows through the mutual matches and not the one-way matches. Alright, I've included all the other matching algorithms, which is sift and surf, right? So a total of 3, op, sift and surf, all into one code. It is exactly identical to the others. All we have is creating the matching object, the brute force matcher, then find the key points, draw the key points, and then show the results. And then this is repeated 3 times. One for orb, one for sift, and one for surf. So if we just run this now, and as you can see, we have all 3 algorithms. This is orb, this is sift, and this is surf. Just visually inspecting the thing, orb seems to be very clean, having minimal amount of matches, and they seem to be decent matches. Surf has a lot of extraneous matches, including on the test track in the lab, and sift also the same, matching against the background template. Alright, next I'm going to draw a polyline, the polyline function, as well as the find homeography, as well as the perspective transform functions, so that I can get a map of the original points of the source image together with the new destination points of the challenge image, and then we can create a map of how do I draw a box to perfectly encompass match that we found in the picture. We only take the top good matches. In this case, I'm picking top 20 because looking at the results earlier, we want to weed out all the extra non-ideal results. Alright, as you can see, we have orb here, sift and surf. Orb has a very nice bounding box around the symbol it has detected. Sift has a line across because of these extraneous data points, right, that cause the perspective to result very poorly, and surf is just a big mess. But either way, we're going to proceed with the creating the next matching with all 3 algorithms as well. Alright, this is the final code that we're going to work with. First of all, this code combines all 3 algorithms into one. Selectable on top is the mode. So if I change this to orb, it will run the algorithm in orb mode, in sift mode, and surf in surf. We'll start from the bottom where the code runs. First of all, instead of selecting individual templates, I'm loading in every single template into a list, and this list actually contains both the template and the template names. The templates then need to have their key points and descriptions generated, and that's what this function does. You just pass in the templates and the template names, and it returns the key points and descriptions for each of the templates. Then we're going to take all these key points and all these descriptions, and then we're going to run the detection algorithm on it. Detection is done in this function. I'm going to use the sift detection as an example. We load in all the template names as well as all the descriptions and the key points of all the templates. So these templates contain all of the symbols that we pre-trained. We're going to generate the key points and descriptions for the challenge image or the image under test, and then we're going to compare this key point and description of the image under test against all of the key points and descriptions of the templates. And we're going to take the average of each individual check. Then we're going to sort the averages to find what is the best match. So we're just going to assume that the match with the lowest average is actually the correct match. So now that we found the correct match using this averaging, we're going to send the correct match over to show result. Over here in show result, we attempt to do the perspective transform as long as we have enough points matches that we are able to do the perspective transform. This will prevent the program from crashing if we didn't find enough matches. And then we use an threshold based on the algorithm being used, because each algorithm has a different threshold. This is to reduce the number of false positives picked up from the background. Depending on which template that we have matched against, we show an appropriate output. For example, if we found the button, we're going to put a button. And for shape, we're going to do something a bit special. We're going to pass the image along into this function called count shapes, where we're going to load in shape symbol and we're going to run the shape detection on it. Due to the shape having a border around it, if I just use this image as is, I'm going to count an extra square, which is the border for the symbol. So I'm cropping away the inner 8% to only leaving the shapes in the center. I'm going to run contours to find the approximate shapes, and I'm just going to print the result back onto the shape and then show the image out to the user. So let's run this. So as you can see the algorithm working here, it is detecting the correct symbol from my phone and then showing the appropriate result. Alright. I'm just going to show a few and I'm going to move on to the other algorithms. This is an example with SIF. In testing, SIF works the best. The important aspect as well as is that all of the background information behind the frame is not being picked up as false positives. Oh, and I almost forgot the shapes counting. Right, as you can see if I hold it steady, it's counting 3 triangles, 2 squares and 3 circles. While initial test seems to show that all produced clean results, SIF was way more stable, as reflected by the data in my report. Either way, the solution works well and is able to identify any symbol live. Both tasks were well accomplished and I've learned a lot. If you run into compatibility issues while reproducing my results, please visit my GitHub. I've listed every single version of the libraries I've used there. Do note that I've compiled most of the libraries from source, and you will have to too. Thanks for watching.